All right, let's continue. Number 7, you have a surface. Ooh, that's the first one with a surface parameterized as follows. So you have R of UV is equal to this. All right, the first one says sketch and identify. You remember how you have you gain an idea of what the surface looks like? Yeah, you look at U and V carefully, and since you have cosine and sine, there's probably some circle involved with X and Z, right? And you try to find the relationship between X and Z because they have cosine and sine. And so if you square both and add them, you get something, right? And then V seems to be sort of independent. This is only appearing in the middle or the second component, second coordinate. So y is equal to v. That's independent. So y must go from 1 to 4, 1, 2, 3, 4. That's all you have. And then the other one, you can tell this is it's 4 cosine square plus 4 sine square, and that's 4. And so that must be a circle here. And since y is independent, it has to be a, a circular cylinder. All right, and I will show you what it looks like in a little more detail. And then part B, find the area of the surface. Yeah, how do you find the area of the surface, area of a parameterized surface? Um, the definition of a surface area is basically this. But in order to calculate this, you would have to find, I hope you remember, you have to find the absolute value or the norm of RU cross RV, because that is the, remember that's a part of DS, and this DS is actually this times dA, where A is this region in the UV plane. All right, so that's my strategy. Okay, let's look at how I am to do this. Number 7. I first write down the, or just copy the parametrization. I notice here that x squared plus z squared is 4, right? So that means it's the radius 2 circle, right? And this is, and then y is independent, and it goes from 1 to 4. So here's the picture. It is a circular, a cylinder that goes in sideways. Of course, this is x and this is y and this is z. All right, so it is a horizontal circular cylinder of radius 2, and the length is 3 because it's y goes from 1 to 4. All right, I take RU, I take RV, and I take the cross product RU cross RV, which by the way is going to give you something normal to the cylinder at any given point UV, right? And so you can go ahead and find your cross product, which looks like this. And then because we are looking for the surface area, we have to find the norm of this RU cross RV. And that turns out to be the square root of 4, which is 2. That's what you have to integrate. So you integrate now in that domain D on the UV plane. And so, I mean, U goes from 0 to 2 pi, and V goes from 1 to 4. And so your region, um, your region is, I think we call it D, the domain, is consisting of a 3 by 2 pi rectangular region on the UV plane. And so you just integrate this, and then you get the answer 12 pi. Right? And that is the area of this. And by the way, there is another quick way of finding the area of the cylinder, right? Because if you have a radius 2, okay, so here's your cylinder, just cut it like this and open it up, and it just becomes a rectangular piece of paper. The length is 3, and then the circumference here is, well, the radius is 2, so this must be 4 pi. Remember, the circumference is 2 times the radius times pi, and of course, this piece of paper is has the area of 12 pi. The geometry stays the same, even though if you are just cutting this and flattening this. Okay, so let's go to number 8. All right, number 8 says you are to evaluate the surface integral f ds. Okay, so f is a clearly a real valued function. That's what this is. It's z. And then s is parameterized this way. All right, so what kind of a problem is this? Is this a flux problem? No, there's no flux involved in this because capital F, you don't have a vector field, right? This is a real value. So this is almost like if you have to come up with a problem for which this is an answer, It could be something like a density and the mass problem. What's the mass of this object S, which is the parameterized cone, if the density is F, which is Z? Okay, that this integral would answer that question about the mass of this parameterized surface S. Okay, so the parameterization is given, right? And then U goes from 0 to 3, and V goes from 0 to 2 pi. And so everything we need is given here, right? What do you have to do? You have to write F in terms of not X, Y, Z, but in terms of, U and V. But look, Z is the last component of this, which is just U, right? So this will be just U. And then what do you have? Well, you have to figure out RU cross RV, right? And then you take this dA, and of course this dA, or the domain D, is going to be the rectangular region defined by these U and V values. All right, so let's look at let's take a look at the answer. F is just Z, all right? So Z in this parameterization is simply U, right? And so I see U. Of course I see U, right? F is Z, which is U. And so that goes right here, right? Now the rest of that, everything else after the double integral sign is the norm of RU cross RV. So in order to find that, I have to differentiate this with respect to U, and then V and cross product must be found. So I typically write it this way: what RU right on top of RV, so I can, with my eyes, go like this times this minus this times that. That's this. And then I go this minus this, and then put the negative sign in front, and then this minus this, and write all that. And the cross product will be this slightly complicated expression. You take the square root of the sum of the squares of each term, which looks like this. And notice here, U squared can be factored from all of these. Okay. Oh, yeah. And then you can write down your answer. I think something's missing. Hold on a second. Okay, so I did not square this cosine, but it should be squared. So there should be a square here. And so cosine square and sine square, when U2 is factored, would become 1. And so U2, the sum of the first two terms is U2, and then you have another term of U2. So that's square root of 2 U squared, which is the square root of 2 times U, since U is non-negative. Okay, all right, so that goes in. This is the integrand following U, which is your function f of x, y, z. So you integrate this thing, which is that. This is your entire integrand. You can factor out, or you can move the square root of 2 in the front. U2 becomes 1/3 U to the third, and then plug in 3 and 0 and get your answer. That's 18 times pi times the square root of 2. All right, let's go to number 9. Okay, number nine says, let F be this vector field. S is a portion of the plane. This is a plane, clearly, right? No squares. It's a plane with a normal vector 4, 2, 1. Over the square region, 1 by 1 square region is given, right? You don't have to visualize this one, but you can if you'd like, okay? And I will show you the visualization of this. Find the flux integral, all right? So the flux integral is this, it's f dot ds. Do you remember what this is? You should remember what this is. Because it's flux, you are concerned about the normal component of the vector field f. This is what you're integrating. This is the real valued function you're integrating, f dot n. But remember, n is RU cross RV divided by its own norm. ds is the norm of RU cross RV times dA. So some things cancel. So this can be written as, the way you find these, you should remember to do that. And this is the way to do that, right? This region R, or I think domain D, is on the UV plane. So you remember, you almost always have to find RU and RV if you are, if your problem involves any parameterized surface, or the surface parameterized by U and V. Okay, so let's take a look at the solution. Number 9, here's a picture of this. You do not have to sketch this. It's kind of hard. For this one, you can set this equal to 0, for instance. And let's say if x and y are 0, z will be 12. If x and z are 0, then y must be 6. And if y and z are 0, then x must be 3. And so that's how you can come up with these three intercepts and connect them, because you know this is a plane. And one by one square over which you integrate this, or over which this plane belongs, is as shown. Okay, now the parametrization was not given. So how do you find the parameterization? Well, if z is given as a function of x and y, remember there is a standard way to parameterize this. You can let u be x, v be y, and z be whatever that expression is where you replace x with u and y with v. And so that's exactly what you see here. You take ru, which is 1, 0, -4. RV is 0, 1, -2. You take the cross product, surprise, surprise, you get 4, 2, 1. Why is it not a surprise? Of course, it's not a surprise because the surface originally was given this plus 1 is equal to 12, right? And you know that this is z, by the way. 4, 2, 1 is normal to this plane, right? So that's exactly what you find. No surprise there, really. Okay, and so that is my vector ru cross rv. I do not have to take the norm of this, right? Remember, because this should be dotted with f. F is y negative x 0. This is y, okay? And this is x, so negative x will be negative u. And so you take the dot product of this f and the just discovered ru cross rv. So that's this dotted with this. That's 4v minus 2u. That's it, all right? And so that's what you integrate over the square region, 0, 1, 0, 1, on the uv plane, which is, of course, the same as xy plane in this case, and you will get your answer of 2 minus 1, which is equal to 1. All right. So the calculation, I mean, this part, I'm not going to spend much time on this because you can do this on your own. That's the easy part. Okay, number 10, S is this surface, which is, well, X is constantly 0. Ooh, that means it must be on the YZ plane, okay? And then you are given this y squared plus z squared is not just equal to 9, but less than or equal to 9. Well, that's not just a circle, but it's a circle with all the interior points. So it is called the disk, right? The disk of radius 3, and it is vertical because it involves y and z. X is constantly 0, so it is on the yz plane centered at the origin. And let C be its boundary circle. All right, so you should be able to draw that. And then you are given F, which is a vector field. All right, now we have to use Stokes theorem to evaluate this double integral. Now this happens to be the flux of the curl of F, but you remember what the other side is? Yeah, the other side is the work integral, the FDR over the boundary of this circle. Right? And so basically, the problem is telling you with a hint, hey, use Stokes theorem, hint, hint, just find this because that must be equal to this double integral. And not sometimes I give you a hint. It says you don't even have to parameterize the surface S. You don't even have to find the curl of F because as long as you can find this, you know how to do that. All right, so this will be R prime. Okay, so what do you have to parameterize? Yeah, what I have to parameterize is actually that circle, right? So let's take a look at that picture and see how to parameterize this. You are given that the x is equal, the x coordinate is always 0. So this is this, vertical disk of radius 3. And I say it's a disk because when you say a circle, technically a circle is the set of all points equidistant from the point, and that has to be just the circle, the outside, the circumference points. Everything inside, if you want to include it, should be called a disk. All right, so F is given here. And how do you parameterize this, circle of radius 3? Well, x is 0, so it has to be 0 first. And then in order to describe the radius 3 circle on the YZ plane, then you would say 3 cosine t, 3 sine t, t goes from 0 to 2 pi. Take the derivative of it. You do not have to find the norm of the derivative because you are going to dot this f with r prime, right? F can be written, x is this, 0. Y is, the second component is negative z. So that's going to be negative of this. And then the third component is y, which is 3 cosine t. All right, so you take that, these two lines, take the dot product of these, and you get 9 sine square plus 9 cosine square. How nice. It is just 9. Okay, so all you have to do is to integrate this thing, which is just 9 over 2 pi, and that answer is going to be 18 pi. All right, now and this is the way to solve number 10. But if you are really interested, and you may be because you are studying for a test, and any practice, additional exercise you can do may be beneficial. So you may actually want to integrate this. Okay, find the curl, find the normal, and take the double integral. Okay, you can do that, and I am showing you how to do that here. If you want to parameterize that disk D, you can parameterize it. Remember, x is always 0. But the y can be written as u cosine v, and the z can be written as u sine v. Because the radius goes from 0 to 3, your u has to be 0 to 3, and v, of course, goes from 0 to 2 pi, right? And then f is x negative z y. If you take the curl, you will see that this will be 2, 0, 0. All right, and then you do rv, take the cross product, based on this parameterization, and this will be u 0, 0. Well, that's nice because you can take the dot product of these, and that's going to be 2u, and that's all you are going to integrate. That will be 2u here. So 2u is your integrand, and so if you integrate this with respect to u, you get u squared. Going from 0 to 3 will give you 9. 9 times 2 pi is 18 pi, right? It's good to have this great feeling, right? The feeling that, hey, I've got this right because I did this in 2 different ways. I'm supposed to have received the same answer, and I did, 18 pi, great. It is really frustrating, however, if you get the 2 different answers. Then you may be in for a long, long day trying to find the correct answer. Okay, but here is the answer here. Okay, let's go to the last question. The last question is, capital F is 2x, negative x plus z, and y. Okay, using the divergence theorem, we are supposed to find the flux of F across the boundary set. Now, it says use the divergence theorem, right? So I'd better have some solid E, and I do, okay? It turns out to be the unit cube 0, 1 times 0, 1 times 0, 1. So it's a 1 by 1 by 1 cube located at the origin. This is 1, this is 1, this is 1. And so the flux over S, flux is going to be, how do you find flux? Okay, that's always F dot N, right? That is the definition of the flux because you are just, adding up or integrating the normal component. But the divergence theorem says this is the same as the triple integral over the solid E of the divergence of F dV. So you do need to know this statement of the divergence theorem. Now, what is the divergence of F? Well, we'll find out, and hopefully it's not too bad. Let's look at the answer. If you take the divergence, take the partial of this with respect to x, this with y, that's 0, this with respect to z, well, that's 2, 0, 0, and so the divergence is 2. Clearly, this is just 2, and then everything else here is a, if you take the 2 out, the triple integral dv, that's just the volume of this cube, which is 1, so the answer is 2 times 1 and 2. Now, if you want to do this, okay, if you want to do this in normal sense, okay, without using the divergence theorem, what you would have to do is to find your n on the top side and find the flux over n. That would be a double integral where z is equal to 1, and you calculate the flux over the top surface, and then you do the same thing for this side, the back side here, and the bottom side. So that will give you, you'll have to find 6 double integrals. I don't think it's really that hard. make sure that your normal always, shows outside. Like for instance, this is 100, this is 010, and the one in the bottom is 00, -1, and so on. So it is possible to find f dot n for each side, each of the 6 sides, and then add them up. And that's possible. And you will get the answer too if you want to do that. I am not showing you how to do that here in this solutions. All right, and then the last part, and by the way, those are the 11 questions. And then the very last part here says, know the difference between all of this. Man, look at how many D's we have here. dt, dx, dr, blah, blah, blah. And so I have a little extra notes here just to remind you what ds was. This is from the line integral section 2. This is also from that same integral. And PDX, QD, PDX, QDI, these were not partials. These are partials, okay? So just remember there is a difference between them. And then all of these, you should know the difference between these things. I think that is pretty much all you have to know. So the book sometimes confuses these two. DS is simply a way of writing, the surface differential for surface integrals. But in reality, anytime we talk about a surface in three-dimensional space, we use u and v as our parameters. So then ds just changes to this, and this dA has to do with du, dv, or dv, du. And so the real integration actually takes place in the uv plane. Just like the real integration here takes place not with respect to s, but with respect to t, because that's the parameter we use to, to carry out the actual integration or the evaluation of the integral. Now, what in the world is this d capital S with an arrow? Okay, this is like our dr. This is very much like a two-dimensional version of the dr. Okay, dr with a vector was r prime dt. And the s with a vector here, it turns out to be that normal component times dA, right? And so remember, it's n ds. And if you really want to know what this was, remember how you found your s for a parameterized surface. The parameterized surface, you have ru cross rv. This is a normal component, but you have to parameterize it, and that's your n, okay? That's your unit normal. But remember, ds, as you can see here, is this object, the cross product, and the norm of it. And that's why this thing cancels out. And so it becomes simpler, right? So hopefully you will remember all of these before you take your exam, and you should be all set. And as usual, whenever you have trouble, or if you have some questions, feel free to contact me during my office hours, or just let me know when you are available, and I will be happy to set up a Zoom meeting, or arrange for some sort of a meeting. Okay, and you can always write me an email. I'll try my best to explain to you, what you're asking about, and the answers and so on. All right. And if you have any extenuating and unforeseeable difficult circumstances, personal circumstances, then please let me know, and I'll see what kind of accommodations I can offer you. All right. Well, have a great day, and I will see you later. Bye.